Welcome to the 6th lecture of module 4. In this module we are discussing reactor design for multiple reactors. Before going to this lecture, let us have brief recap on our previous lecture. In the previous lecture we have covered equal size mixed flow reactor connected in series, MFR or mixed flow reactor of different sizes in series. Then we have considered reactor of different types connected in series. So, mostly the flow reactors, either they are continuous star tank reactor or the plug flow reactor, how their sizes when they connect in series, how their sizes influence the conversion, or for a conversion what are the total volume required, that we have covered in our last lecture. In this lecture we will consider recycle and autocatalytic reactors. The brief outline of this lecture would be recycled reactor, then autocatalytic reactor, and we will compare the sizes for PFR versus MFR, plug flow reactor versus mixed flow reactor, and different reactor combination. So, let us start with recycled reactor. What is recycled reactor? We can see in certain situations it is advantageous to separate the or to divide the product stream into two streams, and part of the product streams is recycled back to the reactor entrance. So, the part of the liquid which is recycled can be defined with the recycled ratio. So, let us consider this is the volume of the reactor V, and it is recycled part of it to the reactor entrance from point H to point G. So, the product which is coming out, it is divided into two streams. One is the product which is taken, and one is recycled which is comes to point G, which is meeting with the fresh feed. So, the recycled ratio R is defined as volume of fluid returned to the reactor entrance divided by the volume of the living streams. So, it can be thought of to vary the recycle ratio from 0 to infinity. That means R can be varied from 0 to infinity or infinite. So, this reflection suggests that the plug flow reactor, when there is no recycle, it behaves a plug flow reactor. When some portion is recycled and fed to the reactor entrance, degree of mixing inside the reactor is increased. That means, as we increase the recycle ratio, the behavior of the plug flow reactor approaches to the CSTR. So, the degree of mixing increases, and at R tends to infinity, the behavior of the plug flow reactor will be as MFR. mixed flow reactor. Now, let us quantitatively see how this happens. So, let us take plug flow reactor of volume V, and where the inlet to the reactor is Fa naught is the molar flow rate in, V naught is the volumetric flow rate of the feed, and its conversion is Xa naught. Then the exit to this reactor is Xa2, and part of the material is recycled here and coming to this point. So, from point H and to point G. Now, when part of this material is recycled, the volumetric flow rate which is coming out over here is Vf. So, the material which is recycled back is RVF, part of the total flow which is coming out from this. So, V3 in this A would be equal to RVF, and its molar flow rate is Fa3. So, due to this addition of the recycled feed, this Fa1 would be Fa naught dash, which is coming with the fresh feed and with the recycled feed, and the volumetric flow rate is V1 and conversion is Xa1, because with the fresh feed, say with Xa naught is the conversion, then you have some converted feed which is coming over here. So, it will change to Xa1. The flow which is coming over here is R plus 1 Vf, and the material or the product which is taken out over here is Xaf, which is equal to Xa2, which would be equivalent to this over here, because same outlet product is recycled back to the reactor entrance. Now, let us do the material balance. So, over the reactor, if we do the material balance, we can write in would be out plus disappearance. So, in would be Fa naught dash, which is over here, and out would be Fa naught dash plus dFa, plus disappearance is minus Ra into dV. So, we can write from here is minus dFa would be equal to minus Ra into dV. Now, in terms of the conversion, this would be minus d Fa1, we can write Fa naught dash into 1 minus Xa, which is equal to minus Ra into dV. Now, from this we can write, if we integrate this one, we can write Fa naught dash integral Xa1 to Xa2, which is Xaf dxa, would be equal to minus Ra integral 0 to V dV. So, from this we can write V by F A naught would be equal to integral x A 1 to x A 2, which is x A f dx A by minus R A. Now, here F A naught is not known, and also the x A 1, which is over here. So, F A naught dash and x 1 is not known. So, until these are some relation can be obtained with some known quantities, the integration is not possible. So, let us find out how to calculate F A naught dash and x A 1. So, for epsilon not equal to 0 and there is a split at point H. So, we can write F A naught dash is equal to A, which would enter in an unconverted recycle stream plus A entering as fresh feed. So, this is equal to R F A naught, which is coming over here, plus F A naught. So, this would be equal to R plus 1 F A naught, and x 1 x A 1 is equal to 1 minus C A 1 by C A naught divided by 1 plus epsilon A C A 1 by C A naught. Now, C A 1 is equal to F A 1 by V 1, which is equal to F A naught plus F A 3 divided by V naught plus V 3, that is volumetric flow rate. So, this we can write F A naught plus R x A f divided by V naught plus R V f, which is F A 3, which is V 3. So, if we write this, then C A 1 would be equal to F A naught plus R F A naught into 1 minus x A f divided by V naught plus R V naught into 1 plus epsilon A x A f, and from here we can write F A naught by V naught into 1 plus R minus R XAF divided by 1 plus R plus R epsilon A XAF. Now, if we substitute this CA1 with our earlier relation, that is XA1 is equal to 1 minus CA1 by CA naught divided by 1 plus epsilon A CA1 by CA naught. If we substitute this CA1 over here, we can get XA1 would be equal to 1 minus 1 plus R minus R XAF divided by 1 plus R epsilon A XAF divided by 1 plus epsilon A into 1 plus R minus R XAF divided by 1 plus R epsilon A XAF. And if we solve, this would be equal to R by R plus 1 into XAF. So we got the relation between XA1 which we need, and also we got FA naught dash. So both the relations we can put into the integral and then we do the integrations. So finally, with this XA1 values, if we consider for any epsilon A and the conversion, initial conversion is 0, we can write the performance equation for CSTR as V by FA naught would be equal to R plus 1 integral R by R plus 1 into XAF. This is XA1 as we have derived, to XAF dXA by minus RA, and this relation is valid for any epsilon A and XA naught equal to 0. Now, if we consider CA1 for epsilon A equal to 0, we can write CA1 is equal to CA naught into 1 plus R minus R XAF divided by R plus 1. So, for epsilon A 0, then this CA1 we can write CA1 would be equal to CA naught plus R CA naught into 1 minus XAF divided by R plus 1, which is equal to CA naught plus R CAF divided by R plus 1. this is Ca1. So, with this limit, if we write for any epsilon A, the performance equation for the recycled reactor we can write as tau is equal to Ca naught V divided by Fa naught would be equal to minus R plus 1 integral Ca naught plus R Caf divided by R plus 1 to Caf dCa by minus Ra. This relation, as we said, is valid for epsilon A is equal to 0. Now, this two expression, this in terms of the conversion and in terms of the concentration, we can show graphically. So, for V by Fa naught is equal to R plus 1 integral R by R plus 1 xaf to xaf dxa by minus Ra, and this is for any epsilon A. So, if we do the general representation graphically, and if we plot 1 by minus R versus conversion, so this would be initially the conversion is, because it is recycled reactor, there is some conversion, and conversion will, so initially because of recycled reactor there would be some conversion at the beginning, and conversion will little bit drop and then it will increase. So, the values of this would be xaf. Now, if it is plug flow reactor, the integral term, this is the integral term of the performance equation of the recycled reactor. So, in that case from A it is limit from R by R plus 1 xaf to xaf. So, if we consider this is R by R plus 1 xaf, so this gives the volume, the area under this curve is represents the conversion under this area under this integral, and if recycle is increased, so at the, if we consider the overall V by Fa naught, it will take the volume which closely resembles to the CSTR, the other part. So, this would be probably the average height, and the total volume requirement for this recycled reactor, and this part from here to this is R plus 1, and this part is 1, and this part is R. Now, if we plot for the special case when epsilon A is equal to 0, so we can see that this is for the special case, and the performance equation is tau is equal to Ca naught V by Fa naught is equal to minus R plus 1 integral Ca naught plus RCAF by R plus 1 2 CAF TCA by minus RA, and this is for epsilon A is equal to 0. Now, if we plot this minus RA minus 1 by R versus concentration, so the plot would be like this. So, means you start with a certain concentration, that is Ca naught, and the final conversion is at say CAF. So, the integral term is from Ca naught plus RCA by R plus 1. So, this is the integral part, area under this curve. So, this would be CAF Ca naught plus RCAF divided by R plus 1. So, the average area requirement for this is about this. So, this is the tau, which is the area, and recycle ratio. So, from here, from this point to this point is R plus 1, and this part is R, this part is 1, and this part is R. So, this is for the special case when epsilon A is equal to 0, and this is the general representation of the recycled reactor performance equation graphically. Now, if we consider recycled reactors, there are two extremes we can consider. Two extremes. What are those two extremes? One is this recycle ratio, we can vary R is equal to 0 to R is equal to infinity. So, for this special case, if we write this performance equation, V by Fa naught is equal to R plus 1 integral R by R plus 1 XAF to XAF dXA by minus RA. These two special case, we can write R is equal to 0 and R is equal to infinite, two extremes. So, if R is equal to 0, it will behave completely plug flow reactor. So, we will get the performance equation V by Fa naught would be equal to integral xa naught to xaf dxa by minus Ra. So, this is PFR, and this equation would be V by Fa naught would be equal to XAF by minus Ra. So, this is mixed flow reactor. Now, this can be seen graphically. We can see the overall volume requirement as we have done before. If we have very small recycle, it will behave like a plug flow reactor, and we can plot say 1 by minus R versus XA. So, which will vary from 0 to XF, and the conversion will change like this, and this is XF. And so, if our recycle is very small, so we can consider this is our recycle up to this. So, this is R, and this is there is no recycle, this is 1. So, this is behave like a plug flow reactor, and the total is R plus 1. So, the area under this curve is the plug flow reactor area volume requirement, and this area would be the CSTR area. So, the average area requirement would be something about this. This is the average area requirement. But in this case, if we consider large recycle, so this is for small recycle. For large recycle, it would be 0 to XAF, say over here, and our recycle is very large. So, we will keep up to this, say so this is recycle, and this part is 1 not recycle. So, total is R plus 1. So, the rate versus conversion curve under this would be the PFR volume requirement, and the rest of the part, because of large recycle, it would be the area requirement would be high. So, because it will behave like a CSTR. So, the average area requirement would be high compared to small recycle. So, this is for large recycle. Now, if we consider first order reaction, for first order reaction we can write the performance equation Ca naught V by Fa naught is equal to minus R plus 1 integral Ca naught plus RCAF divided by R plus 1 CAF DCA by KCA. This is for first order. So, if we integrate, we will get K tau by R plus 1 would be equal to minus ln CAF into R plus 1 divided by Ca naught plus R CAF. So, this is nothing but K tau by R plus 1 would be equal to ln Ca naught plus RCF CAF divided by CAF into R plus 1. So, now if we take the ratio between the space time or residence time or their volume ratio of recycle reactor and the plug flow reactor, we could see for the first order reaction from here, this is Levenspiel plot, and we can see that when there is recycle is large, it behave like a mixed flow reactor MFR when R tends to infinite. So, over here the volume requirement becomes large. When recycle ratio is reduced, it goes to close to plug flow reactor. When R tends to 0, it behaves like a plug flow reactor. So, this is Levenspiel plot. Now, for the second order system also we can get similar information for the Levenspiel plot. So, for second order system, if we consider say twice A2 product, so with minus RA is equal to K CS square and epsilon A is equal to 0. So, we can write tau by R plus 1 would be equal to minus integral Ca naught plus RCAF divided by R plus 1 to CAF DCA by minus by KCA square. Now, if we integrate, it would be K tau by R plus 1 is equal to minus 1 by Ca with a limit Ca naught plus RCAF divided by R plus 1 to CAF. If you put the limit, this would be K tau by R plus 1 would be equal to Ca naught minus CAF divided by CAF into Ca naught plus RCAF. Similar to the first order reaction, we can also take the ratio of the volume required between the recycled reactor and the plug flow reactor, and if we can see that if we change the recycle ratio, then it will goes from when recycle ratio is less, it is behave like a plug flow. When it is high, it will behave like a mixed flow reactor. Now, let us take an example. For an irreversible first order liquid phase reaction where Ca naught is 10 mole per liter, conversion is 90% in a plug flow reactor, if 2/3 of the stream leaving the reactor is recycled to the reactor entrance, and if the throughput to the whole recycled reactor system is kept unchanged, what does this do to the concentration of the reactant leaving the systems? Now, let us solve it. Say initially we had Ca naught is equal to 10 mole per liter, and this is exit is say Ca. Now, as it is said, this is for first order irreversible liquid phase reaction. So, for first order system we know that Ca by Ca naught is equal to e to the power minus k tau. From here we can write k tau is equal to ln Ca naught by Ca. Now, as it is given 90% conversion. So, Xa is equal to 90. So, conversion is 90%. So, Xa is equal to 0.9. So, this is equal to Ca would be equal to, for 90% conversion, Ca would be Ca naught into 1 minus Xa, which is equal to 10. Ca naught is 10 given over here, 10 into 1 minus 0.9, so which is equal to 1. So, k tau would be ln 10 by 1, which is equal to ln 10. Now, as it is said, 2/3 of the stream leaving the reactor is recycled to the reactor entrance. So, from the definition we can write R is equal to volume of fluid returned to the reactor entrance divided by volume of fluid leaving the system. So, now as it is said, 2/3 of the stream leaving the reactor, that means is recycled. So, 2/3 is recycled, and so the volume of fluid which is leaving the system is 1/3. So, R is equal to 2. Recycled ratio we can get over here is 2. Now, with recycle, for recycled reactor we know k tau is equal to R plus 1 ln Ca naught plus R Caf by R plus 1 Caf. This is for first order reaction. We have derived this relation. So, if we substitute the values, say CAF we have to calculate. So, K tau we have calculated earlier, K tau is equal to ln 10, which is 2.3. So, if we substitute, 2.3 is equal to 2 plus 1 ln Ca naught, which is 10 mole per liter. So, 10 plus recycle ratio we have calculated 2 into CAF divided by recycle ratio plus 1 into CAF. So, if we simplify, this would give CAF is equal to 2.24, or we can write from here XAF would be equal to 0.776. So, if we keep the throughput through the whole recycle reactor unchanged, it will change the exit conversion to 0.776. So, the final conversion will be reduced. Now, take another example. At present, there is 90% conversion of a liquid feed, N is equal to 1, Ca naught is equal to 10 mole per liter to a plug flow reactor with recycle of product, and recycle ratio is given R is equal to 2. If the recycle stream is shut off, by how much will this lower the processing rate of the feed to the same 90% conversion? So, basically recycled reactor later converted to the plug flow reactor. So, let us solve this. So, this is since N is equal to 1. So, this is first order reaction. So, for first order reaction we know the K tau. K tau is equal to R plus 1 into ln Ca naught plus RCAF divided by R plus 1 CAF. Now, if you substitute the values, R is 2 plus 1 ln Ca naught is 10 plus 2 into 1, because 90% conversion. So, for 90% conversion XA is equal to 0.9 as we did before, CAF would be 1. So, we can write 2 into 1 divided by 2 plus 1 into 1. So, this would give 3 ln 4. So, 12 divided by 3. So, ln 4. Now, with recycle, this is with recycle. Now, without recycle, that means it is PFR. We can write K tau is equal to ln Ca by CAF, which is equal to ln 10 by 1, which is ln 10. So, if we take the ratio there K tau. So, this is without and this is with recycle. So, if we take tau without by tau with, it would be ln 10 divided by 3 ln 4. So, this would be equal to 2.3 divided by 4.16. So, if we take this ratio, this would be 0.55. So, hence we can write tau without would be equal to 0.55 tau with recycle. So, that means we can see that without recycle is better. So, without recycle is better. So, now we will discuss autocatalytic reaction. As we have seen, for any positive order reaction, for batch reactor we have seen that as the reaction proceeds, the concentration drops and the reaction rate decreases. So, the rate changes progressively as the rate decreases progressively as the reactant concentration is decreased. But in case of autocatalytic reaction, the reactants reacts with the product which is formed and then the reaction proceeds. So, reactions become faster. So, in this case what happens, at the beginning we need to have certain products, so that which can react with the reactant and form the product again. So, autocatalytic reactions, if we consider the rate versus concentration change, say this is minus Ra versus Ca. Initially, when the reaction starts at a high concentration, starts with Ca naught, and the reaction rate increases progressively and then it decreases. So, basically it starts with Ca naught. Initially there are very small quantities of the product is present, then the reaction starts, the rate increases progressively and then it reaches maxima. So, this is basically if reaction can start without any product. Say if we consider A plus R produces R plus R with a rate minus Ra is equal to K Ca to the power A Cr to the power R, and if the reactions can start without the product, it will be very low rate initially, and as soon as the product will form, then they will react and the rate will be faster. So, this is for no product R. Now, if we have some product present at the start of the reaction, so this rate could have been started at higher, and then the rate could have been like this. So, this is with some product present, and the progress of the rate is like this. Now, this autocatalytic reactions leads to a very interesting optimization problem, as we can see, because it gives maxima or minima. Once it reaction starts, it reaches to a maxima or minima and then goes to completion. So, if we plot minus 1 by R A versus X A conversion, the plot would be like this. So, this would be the maximum point of rate. So, this is the progress of the reaction, and this point is the maximum rate. If we consider plug flow versus mixed flow and no recycle, in this case we can see that if we plot minus 1 by R A versus X A, so the plot would be like this. And the conversion, if we take this is XAF, so this is MFR and this is PFR. Now, 3 cases we will see. In another case, so if we take the conversion, initial conversion is high, say XAF, so the CSTR would take the volume this much, whereas PFR will take the volume this one. Now, if we take very high conversion, say so this is the volume required for CSTR, and the PFR volume would be this much. So, we can see that at low conversion the MFR would be superior, as we can see that the volume requirement for CSTR would be small compared to the plug flow reactor volume. So, if we go to moderate conversion, say XAF, at high conversion, here we can see PFR is superior compared to the CSTR, because the volume requirement for PFR is small compared to the CSTR. and this finding differ for ordinary nth order reaction, that is n greater than 0, where PFR is always greater than MFR. So, it may be noted that PFR will not operate at all with pure reactant feed. As we can see, for autocatalytic reaction, the reaction should start with certain percentage of or certain concentration, minimum concentration of the product, because which will initiate the autocatalytic reaction. So, this is ideal for the recycled reactor. So, in this case, feed must be continuously primed with product, an ideal opportunity for the recycled reactor. Now, we can calculate the optimum recycle ratio. The optimum recycle ratio we can calculate from the earlier equation that we have derived, tau by Ca naught for recycled reactor would be equal to integral xai, which is equal to r xaf divided by r plus 1 xaf r plus 1 by minus ra dxa, and if we differentiate this equation, that means d of tau by Ca naught dr and set it to 0, we can obtain the optimum recycle ratio, and this can be done using the differentiation under the integral, which can be done from theorem of calculus. As we know, Fr is equal to function of r is equal to integral Ar to Br function of x r dx, and then if we differentiate this relation, it would be df by dr would be equal to integral Ar to Br del f x r del r dx plus f function of b r db by dr minus f a r dA by dr. So, this is Leibniz integral rule. For variable limit of integration and special case would be constant limit of integration. Now, if we apply this same thing in this case, this would be d tau by Ca naught dr would be equal to 0 is equal to integral xai to xaf dxa by minus ra plus 0 minus r plus 1 divided by minus ra. This is at xai dxai by dr, where dxai by dr is equal to XAF by R plus 1 square. So, if we combine this and rearrange this relation, we will obtain 1 by minus R A at XAI would be equal to integral XAI to XAF dXA by minus R A divided by XAF minus XAI. So, in other words, we can see that the optimum recycle ratio introduces to the reactor a feed which 1 by minus R A value equals to the average value. This can be seen graphically. So, if we plot 1 by minus R A versus X A, we could see that if recycled is very high, then for this particular type of rate concentration curve, this is say XAI to XAF and this is XA naught, this is area under the integral. So, the average height would be say this much, say L1, and if we take see high XAI values to XAF, then this is XA naught, this is the area under the curve and this is the average height say L2, and recycle is very low. So, that means say XAI to XAF, so the area requirement which is XA naught, so this is PFR and the average height is say somewhere here, say L3. The first case is recycle is too high, this is recycle is too low and this is recycle is optimum. Now, if we consider combination of the reactors, say if we have plug flow and the CSTR, we can always look into the arrangement of the PFR and CSTR arrangement in such a way that the total volume requirement for autocatalytic reaction is minimum. Say if we consider these two cases, say we have mixed flow reactor where we have CA naught, this is MFR, then outlet from here is going to a PFR and finally we are getting CAF. This is PFR. In this case, the product which is we are getting is not separated and is fed to the PFR. So, the overall volume requirement in this case is minus 1 by RA versus concentration if we plot, and the nature of the curve is like this, autocatalytic reaction. So, we can say this is CA optimum. So, this and our initial start of the concentrations is CA naught. So, we will look for CSTR, this one, and rest to CAF. So, this is PFR. Now, if we have option to separate the product and recycle back, in this case we can see that, say if we have CSTR and the product which is coming out is separated here and recycled back to the reactor entrance. So, this is recycled reactor. MFR and this is separator. So, you can separate the product CAF. So, in this case we can see that the volume requirement would be, so this is optimum and this is the CA naught. So, we can see that only MFR volume up to optimum concentration we can run with a CSTR with recycle. So, looking into the rate concentration curve and the options available in hand, whether we can separate the product and then recycle back, or without recycle whether we can process it, depending on that we can decide which option to choose or which would be more desired design or optimum design. So, thank you very much for attending this lecture, and we will continue our discussion on the reactor design part in the next lecture.